Hello and welcome to this section of the Physics 3 tutor. In this section we're going to work some problems dealing with charge carrying wire or a current carrying wire in a magnetic field, just to give you some practice. So the first problem goes like this. A straight stretch of wire has a current of 27 amps. What is the magnitude and direction of the magnetic field B needed to float the wire? The linear density of the wire is 45 grams per meter. Now I promise you this is a great example of a very simple problem. You'll see there's not much math, but you must understand what's being said or you're just never going to get the right answer. This is really what 99% of physics is about. We want to float this wire. How can we float a wire? That means we have to have a force exerted on it enough to balance its weight, right? That's really what we have. Now they're given this weird thing, linear density of wire, grams per meter, 45 grams per meter. I never taught you anything about that. So a lot of times you read it in the book and you're like, boy, I don't understand that. You need to just take it one step at a time. So let's draw a picture and see if we can understand it. You can draw the picture any way you like, but this makes sense to me. This is the wire. It's a cylinder, right? I'm going to put a dot in the center just to remind you the wire is actually coming to you. So it's not drawn obliquely, it's coming straight out of the board. All right. Now this wire has a weight, right? A force of gravity, right? Which is mg. Mass of whatever segment of wire that we have that we're talking about times gravity. And what we want to do is actually, we want it to float somehow. So we know that the force going up needs to be the same length as the force going down. So this is going to be FB, going up like that. All right. So the first question is, before we do any math, what will the magnetic field look like to do that? Okay. So you start going different directions, putting magnetic fields with your pencil different directions. But if you think about it, if the magnetic field goes this way, let's draw that and see what happens. What if the magnetic field goes like this? Since I've drawn it with a dot here, the wire is coming out of the board carrying a wire, carrying a current coming out of the board towards you. So the vector, the L vector, is coming out of the board because the current is going that way. So what it would be is, it would be IL, which is this vector here, crossed with B. IL cross B means a force is going to be going up. If you flipped it this direction, it would be IL coming out like this, going that, and then it would be pushing the guy down. You don't want that, so you want to flip it this way so the force is going up. So we know the direction of the magnetic field needs to be a horizontal magnetic field in relation to how I've drawn it here. Now we just need to do the math. So in order for this to work, for this floating to work, the force pushing up must equal the weight of the wire coming down. This is really the crucial equation to understand that that needs to happen. So the force, forgetting about the vector cross product version, we just talk about the magnitude, ILB sine of phi, that's sort of the general version, is equal to mg. All right, now this is the force exerted by the magnetic field. This is the weight of the wire. Now we know, really, ILB times the sine of, this is the angle between L and B. The angle between this guy and the magnetic field B is 90 degrees. So what happens really is the sine of 90 is 1, so this really just drops out. So what we really have is ILB is equal to mg. ILB is equal to mg. So what we're trying to do is find out what strength of magnetic field we need. So let's solve for B, mg over IL. Now at this point we solve for the magnetic field and we don't think we've really made any progress because we don't really know the mass of the wire. We do know the current. We don't really know the length of the wire, but we do know G because G is gravity, right? So we think we're kind of stuck because we don't really know what the mass of the wire is and we don't know what the length of the wire is. But then we go back to our problem and we see, they gave us something called a linear density. What's a linear density? It means how many grams of mass does this wire have per unit length. So in 1 meter, or in this case it's 45 grams per meter. So that means for every meter of wire, if I take it off of a spool, 1 meter of it, it's going to be 45 grams. If I take another meter of wire off, it's going to be another 45 grams. It's called a linear density. They just do it this way sometimes to make you think a little bit more, basically. So if we go back to our problem, we do not know what the mass of this wire is, and we do not know the length of this wire, but we know the ratio of the mass per unit length. which really, when you think about it, mass per unit length, that's wrapped up inside of what we have. So really, this is equal to mass per unit length times G over I. And I know what these last two things are. So my magnetic field that's required is going to be equal to M mass per unit length. Look at the problem, 45 grams per meter. The problem is you can't use grams because, you know, grams is not something, you usually use kilograms. It's the base unit. So you can't use 45. So just convert that to kilograms real quick. So 45 times 10 to the minus 3. That would be kilograms per meter. So we'll use that number. And then here G is 9.8 and I is given to us as 27 amps. So you see, even though we didn't really know the mass of the wire, and even though we didn't know the length of the wire, we know the ratio. That's given to us in the problem. And that's a trick they do a lot of times in physics to kind of trip you up. They don't really give you everything you think you need. So you think that you don't have enough information to solve the problem, but 99% of the time, either the variables you think you need cancel out anyway, or it's something like this, where you have a ratio somehow and you don't need to know the individual numbers, you just need to know their ratio. So when you do this, when you take the 45 times 10 to the minus 3 times 9.8 divided by 27, the magnetic field required is 1.6 times 10 to the minus 2 Tesla. And it's Tesla because all the units we've been dealing with are base units. We've got, we've got amps, we've got kilograms per meter for this, and so on. So we have the base unit, 1.6 times 10 to the minus 2. The direction is given really by the right-hand rule. It can only point this way in order to give us a force pushing up, which is really what we want. So good problem. This kind of thing really can trip people up. So don't give up. If you think you're on a test and you don't think you have enough info, you do have enough info. You just need to figure out how to put it into a shape so that you can use what you have. All right, the next problem says a wire is 1.8 meters long and carries 13 amps of current, and it makes an angle of 35 degrees with a constant magnetic field of 1.5 Tesla. What is the magnetic force on the wire? All right, what's the magnetic force on the wire? So here we have an angle between the magnetic field and the wire, but we've given all these other numbers, so let's draw a picture and see if we can make sense of this. So we have a wire. We're going to draw a wire more or less like this. We have a current flowing through the wire that's given to us as well. So here is some current I. And then what we have here is a magnetic field. We're told that the magnetic field is at a 35-degree angle. So I'm going to do my best to draw this guy at some kind of an angle here. It's not exactly 35 degrees, but I'll try. And you know, this is whatever, 35 degrees there. Okay, and the magnetic field strength, B, is 1.5 Tesla. So it's pretty cookie cutter really, because we know that the force on any of these wires is equal to ILB sine phi. Sine phi. We don't really care about the direction. We don't really care about the direction of this guy. We're just asked, what is the force on this wire? These guys are not perpendicular to each other, but they do still lie in the plane that's pretty easy to visualize. So when you do the right-hand rule, it's going to be IL crossed with B. So here's B right here, going like this. I is going like this. So if you cross IL cross into B like this, you're going to be pushing the wire into the board. So that's the direction of the force. The rest of the stuff just comes from the diagram. So what we're going to have is the force is going to be equal to I. The current was given as 13 amps. The length of the wire is given to us as 1.8 meters. The strength of the magnetic field is given as 1.5 Teslas. And the angle between these two guys is sine of 35 degrees. So literally, it's sort of plug and chug. 13 times this times sine of this. The force is going to be 20.13 newtons. And the direction you have to get from the drawing, which is into the board. So again, we have, here's I, here's B, and so you're crossing IL, which is L is the direction of the wire and the direction of the current, crossed into B, you're pushing the I into the board with a force of 20.13 newtons. So we did a couple of quick problems to show you how to use this guy. What I want to do is close this section off, let you digest this, and work these problems. In the next section, we'll have a couple of additional problems, maybe of a slightly higher complexity, so that you can get the feel for how to to work problems of different types. But more or less, the general concepts that we've talked about up till now is going to serve you very well for all of the problem types. When we talk about a wire in a magnetic field that's carrying a current, is going to be pushed by the magnetic field. And by the way, I will give you a heads up or sort of a preview of what's to come. If you were to crack apart a motor, right, an electric motor, what you would see inside of it is a bunch of magnets and a bunch of wire. So later on, a couple sections from now, we're going to learn how to construct a coil of wire in such a way that when we run a current through it, a force will be exerted to turn that motor. Instead of to push it or slide it, it'll turn it. So this is really the basis and the foundation of electric motors, which is prevalent everywhere, right? So it's a very, very practical thing that we're learning now that we're going to be able to expand on in the next few sections.